Seismology is the principal tool that we can use to image the Earth's interior. This is a short introduction to the use of global seismology to image the Earth's interior, specifically to study tectonic issues. We're going to look at the basic structure of the Earth, and this will involve ideas beyond seismology. And then we're going to move on to the seismology itself. We'll look at seismic waves, the different types. We'll use these to construct things called travel time plots with a view to creating a reference Earth model. And then we'll look at deviations away from this reference Earth model, which is fundamental to the idea of seismic tomography and imaging structures, particularly within the Earth's mantle. So let's start off with some basic Earth science that predates the development of many seismological ideas. We want to look at how big the Earth is, how dense it is, and therefore the evidence that the Earth has a layered structure. So let's start off with how big. Well, of course, there's a problem with this. We can't really put a tape measure around the world and measure as a continuous measurement the circumference and therefore the radius of the Earth. So what we can do is do it in segments. And the way to do that is to make a measurement on the ground of a known distance and then see how many degrees of circumference this linear distance represents. And this was actually first attempted a long time ago by the Greek philosopher-scientist Eratosthenes in Egypt, using the different angles the sun made at noon to the Earth's surface. However, this really took off in the 18th and 19th century, and the sun was not the only extraterrestrial body against which you could make measurements of angles. Prominent stars were used as well. And the results are summarized in this diagram. The Earth is not a perfect sphere. It has an equatorial radius that is some 20 kilometers greater than the polar radius. In other words, the Earth is slightly bun-shaped. Interestingly, the shape of the Earth is very close to that of a fluid drop that rotates at the same velocity as which the Earth rotates. So this suggests that over a long period of time, the Earth behaves like a fluid. But that's another story. Let's come back to this question of size, and we can take this oblate bun-shaped Earth, and if we consider it to be a perfect sphere, it would have a radius of 6,371 kilometers. Now, the next question is, how dense is the Earth? And we can work this out from the law of gravitation by measuring the attraction of masses at the Earth's surface accelerated through gravity to the centre of mass that will obviously be in the centre of the Earth. And through experimentation, we can therefore estimate the mass of the Earth as being slightly less than 6 times 10 to the 24 kilograms, which is a very large number, but of itself is not particularly interesting. The interesting part of this arises when we divide this mass by the volume of the Earth to find the average density. And that comes out at 5,520 kilograms per meter cubed. Now that value is very interesting because measurements of densities of rocks at the Earth's surface in the crust are all less than about 3,000 kilograms per meter cubed, which means that the crust is unrepresentative of the Earth as a whole. The Earth is significantly denser than the materials we find at the Earth's surface. So the Earth, therefore, is layered. The question is now whether these low-density rocks at the Earth's surface just represent a thin scum, or whether there's internal structure to the Earth as well. And to find this out, we need to think about the moment of inertia of the spinning planet. And we're not going to go into this in detail, but geophysicists were able to work this out using the moment of inertia from the orbital wobble of the planet. The Earth's own spin axis is not perpendicular to the orbit around the Sun. It's pulled over by the Moon, so the interaction of the gravitational pull of the Sun and the Moon generate a gyroscopic wobble in Earth orbit, and the period of that wobble allows geophysicists to estimate the moment of inertia. And the result is we can determine that most of the Earth's mass is located towards its centre. In other words, the Earth is layered as shown in this simple sort of pie slice, with a core with a density of that which is some 14,500 kilograms per meter cubed, covered by an outer shell of material significantly less dense. This outer shell, of course, we call the mantle with its veneer of crust. So the Earth is layered like this. But by applying ideas that date back to ancient Greece, but largely date to Newtonian physics, and surveying through the 18th and 19th centuries, we can establish that the Earth is layered. With a core, a mantle, and a thin veneer of crust. But what are the properties of these layers? Well, this is where seismology comes in. So let's tackle the seismology. We're going to look now at seismic waves and then look at travel time plots. So the seismic waves we're interested in are sourced naturally through earthquakes and, to a certain extent, volcanic eruptions and subvolcanic processes. There are also human sources for global seismology, atomic bombs. More of that shortly. In this, we're going to be looking at seismic waves, and we're going to look at the seismic waves that are transmitted through the Earth. In other words, they're body waves. And there are two principal types of body wave. P waves, which stands for primary wave, and S waves, which stands for shear waves. And these waves behave differently. Let's look at them in turn through a couple of simple animations. So here's a cartoon of a P wave. It consists of a pair of compressional and dilatational components. In the compressional part, the materials are squeezed together. In the dilatational parts, they're dilated. And the wave propagation in this diagram is going to move from left to right. So let's see how it plays out. So here comes the compressional component followed by the dilatational shown by those arrows. And if we imagine there being a seismic station on the right hand side, the first thing we'll see is a compressional arrival followed by dilatation. So that's the behaviour of P waves. You'll notice, of course, that these are elastic waves. Our grid returns to its original shape after the wave has passed through. So let's look at shear waves. In shear waves, the wave motion is in and out of the direction of wave propagation. In other words, perpendicular to the direction of wave propagation. In this particular case, the wave motion is up and down relative to wave propagation, but it could be side to side, in and out of the screen, or oblique. So let's see how this plays. Here we go, running across. Again, it's an elastic wave, so the grid returns to its original shape after the wave has passed through. And there we have it. So, two distinct wave types, P waves and shear waves. So, these have different properties. P waves propagate faster than shear waves. And we can illustrate this with data from granite at 20 kilometers down. Well, granites propagate P waves at almost 6 kilometers per second, whereas shear waves move through granite at 3.5 kilometers per second or so. So shear waves are significantly slower than P waves. The other really key part about shear waves is that they're not propagated through liquids, only through solids. So what controls the seismic velocities through rocks? And it's principally a function of the density of the rocks and their rigidity. Liquids have effectively no rigidity, so shear waves have zero velocity through them. So now let's use these behaviours. So we're going to look at seismograms, in other words, the records collected by seismic stations, seismometers, of earthquakes. Seismometers that are located away from the earthquake focus. And those seismometers record a history of shaking following an earthquake. So therefore we're going to plot the earthquake record against time. Here we go. So here's a seismogram. The first arrival is the P wave, because it moves faster than the shear wave, which therefore comes in afterwards. And of course, there's more energy that's picked up by the seismometer, which dribbles out up to 20-25 minutes later. And this is called by seismologists the coda, which is Latin for tail. And we're not really worried about that here. So for here, we're really just concerned with P wave and S wave arrivals. And you'll notice, of course, that there's a delay in the arrival of shear waves because they move slower through the Earth than the P waves. So they get to our seismic station later. So let's see now what the records are for stations that are located further away from the earthquake. So we're going to look at two other stations, an orange one and a red one, increasing distances away from the earthquake. So let's look at the orange one. There we go. And of course, because it's further away, the energy for the P wave and the shear waves have arrived significantly later than those recorded at the yellow station. And there's a delay between P and S again. So now let's look at the pink station. And again, our energy has arrived at our station later than orange and yellow because our pink station is further away from the earthquake. And there's our P to S delay. So if we compare the P to S delays for our different stations, you'll see that as we move away from the earthquake, the P to S delay increases with distance away from the earthquake. And this is one of the fundamental ways in which seismologists can locate earthquakes in the Earth relative to an array of stations. Well, what we're going to do now is use this information to plot travel time graphs. We're going to plot travel time versus distance away from earthquakes. And we're going to spin this diagram around so that travel time is on the y-axis here. So we've got travel time running up our plot and distance from earthquakes running along the bottom. And there's a little cartoon at the bottom there to show how three stations are organised relative to an earthquake. So let's put on station X records. There we go. And there's a P wave that arrives first, at around 3.5 minutes, and then a shear wave that's arriving, about 6 minutes. So a few minutes later than the P wave. So let's now put on the records from the other two stations. There we go. Again, the P waves arrive first, the shear waves arrive second in each case, and because station Y and Z are further out than station X, then all those signals are arriving later than their equivalents in station X. Now we can use this information to learn a lot about the seismic velocity structure of the Earth. Let's start off with a simple idea that if the ray paths, in other words the direction that the energy is taking through the Earth, are straight and the seismic velocity is constant, there should be a simple linear relationship between the ray path length and the arrival time of the waves. So let's look at how this plays out by plotting a line for the P wave arrival as if it was honouring this simple idea, passing through the first arrival at station X. And if we look at this line, it's forecasting when the P wave should arrive in the other stations. So let's look at station Z. This is the predicted arrival time of our P wave, and a quick look at the seismogram tells us it's not working. The actual arrival time for the P wave at station Z is significantly earlier than that predicted by our simple idea at the bottom there. So let's plot the actual curves for these arrival times. These are travel time curves for P waves and shear waves connecting up our arrivals through the stations. So in red is our travel time curve for the P waves, and the travel time curve for the shear waves is shown in blue. We'll just consider the P wave for now. And the reason that the travel time curves are curved and not straight is that the ray paths are tapping higher velocities at depth. And to explore why that is, let's just step away and think a little bit about refraction. So here's a cartoon. It shows a pair of layers in green, and the seismic velocity in these two layers is different, so that the deeper layer in dark green has a higher seismic velocity. At the interface then, which is abrupt, the ray path will refract, and because the seismic velocity is increased across that interface, the trajectory taken by the ray path becomes lower angle or shallower. Now let's make this slightly more complicated by putting lots of layers in, each of which gradually increases in seismic velocity with depth. And you can see what's happening now is that every time our ray path meets an interface, it becomes lower angle. So that as you go towards the deeper part of our profile in here, the angle taken by the ray path is becoming more gentle. So let's take away the interfaces and just have a simple scenario where the seismic velocity smoothly increases with depth. And this is the ray path that will be formed. It's curved. Eventually, of course, that ray path will effectively reflect back to the surface, so that we end up with ray paths something like this. They curve back to the surface away from a source as long as the seismic velocity increases gradually with depth. The important part about this is it means that the waves that penetrate deeper are accelerated because they're seeing rocks with higher seismic velocities, and more distant stations will receive those waves that are passed deeper into the Earth. So coming back to this diagram in here, we're seeing that the more distant station, station Z, is receiving energy that's passed deeper into the Earth. So the arrival time is earlier than we predicted with the constant velocity model. So these are travel time curves. Okay, so we can now use these to examine Earth structure. And we're able to do this largely because of the Cold War. As nations acquired the technology for atomic bombs, there was a need not only to detect tests, but also to verify various test ban treaties. And as a consequence, through the 1950s, 60s and 70s, a global array of seismometers was put out. And these could detect not only atomic bomb tests, but also, of course, earthquakes. And those earthquakes with magnitudes of greater than 5 or 6 could be detected all around the world by these seismometers. That's many hundreds of earthquakes per year. So there's a great record of earthquakes because of this global coverage. What are the results? So what we're going to do is plot travel time curves. Here's our graph again, with arrival time up the left-hand y-axis and distance in degrees around the Earth away from earthquakes along the x-axis. And all the world's earthquakes are plotted on this diagram at the origin. So we're looking at essentially a normalized plot. Let's look at some results. Here's the P wave first arrival result. In these diagrams, conventionally, the travel time curves are labelled by the path taken by the ray. So the P wave that we see on the left-hand side of this diagram is the P wave that's only transmitted through the mantle and then detected back at the Earth's surface. The PKP component of this on the right-hand side is the record of P waves that are recorded on the far side of the Earth from any particular earthquake, out at distances of 144 degrees and greater, and the ray path taken by these events has passed through the core. So the rays went through the initial pit of the mantle, then through the core, then through the mantle again. So the K in here designates that part of this ray path has included transmission through the core. Now the interesting thing about this graph is there are effectively no P waves recorded between 103 and 144 degrees away from an earthquake. In other words, there's a shadow zone. So let's see how this plays out in our cartoon Earth. Here's that shadow zone between 103 and 144 degrees from the earthquake. Now in fact there can be the occasional P wave arrival in here, which is one that's reflected off an interface within the core, but there are very few of those. Most of these P waves are deflected away from this so-called shadow zone. And the reason for this you can perhaps see from this diagram. If you look at the trajectory taken by P waves as they move down in the Earth, those that intersect the core mantle boundary there are refracted, but they refract inwards away from the shadow zone. Refraction at the core mantle boundary with this sense implies that the seismic velocity of the outer core is lower than the deep mantle. There's a velocity drop at the core mantle boundary. Consequently, we have this shadow zone in our travel time curve plot. Now, some of these P waves, of course, will intersect the core mantle boundary and bounce back towards the Earth's surface. In other words, they'll be reflected. So we get these arrivals here, which are labelled PCP. It's a P wave reflected off the core mantle boundary, back towards stations quite close in to the earthquake. Let's put in now the shear waves. Of course, the shear waves are coming in after the P waves at any given station, and as with the P waves, the shear waves also generate reflections off the core mantle boundary and come in there as SCS, travel times. Let's just reinforce this story by looking at an arbitrary station 32 degrees out from the earthquakes. The first one to arrive is the P wave, at about 6 minutes. The next one to come in is the PCP, P wave reflected off the core at about 9.5 minutes. A little bit later, we have the shear wave coming in. That's the first shear wave arrival, at about 11 minutes. And then finally, with respect to these particular waves, the SCS, the shear wave reflected off the core, comes in at about 18 minutes. So that's how this diagram works. So let's draw out a fundamental conclusion now for tectonics and indeed for earth science in general. And that is that shear waves can be transmitted through the mantle. So therefore the mantle is solid. Okay, there may be the odd pocket of magma and so forth in the upper mantle, but overall the mantle behaves as a solid. It transmits both P waves and, critically, shear waves. But the shear waves are not propagated out to stations beyond 103 degrees from the earthquakes. In other words, there's a shear wave shadow zone. So although shear waves can be transmitted through the mantle, they're not transmitted through the core. So at least the outer core is liquid. So those are two really dramatically important conclusions that arise from this seismology. The other one is that all these results work by stacking earthquakes to our origin on our travel time plot. So it doesn't matter which earthquake detector setup we use, we get the same results. So our model is insensitive to earthquake location. The Earth's structure, therefore, is concentric. Okay, that means that because the Earth's structure is concentric, we can summarize these behaviors simply in one dimension, as though putting a straw down from the Earth's surface to the inner core. It wouldn't matter where we drew our one-dimensional profile, we'd always have the same picture. So let's do that. What I'm going to show you is something called the Preliminary Reference Earth Model, and it was put together in 1981 by Jaworski and Anderson on the basis of collecting information from many earthquakes. Many of these ideas were established significantly before 1981, but had to wait the development of the computer power through the 1970s that allowed many earthquake records to be put together. So let's look at this graph. What we've got here along the bottom is the depth. So this is our one dimension from the Earth's surface on the left down to the inner part of the Earth on the right. And on the y-axis, we'll plot various properties, and we can start off by plotting the P-wave velocity. At the Earth's surface, the P-wave velocities, well, within the crust they barely feature on here because of the scale of the diagram, but the upper mantle has a P-wave velocity of about 8 kilometers a second, and it increases in a slightly jerky fashion in the upper mantle until we get to about 700 kilometers down, and then after that it smoothly increases all the way up to the core mantle boundary, although there's a slight kink as we approach that boundary. At the interface between the mantle and the outer core, there's a significant drop in the P-wave velocity, which we saw because of the P-wave shadow zone earlier, and then there's an increase gradually through the outer core and a step up into the inner core. Now let's contrast this P-wave behaviour with that for shear waves. Of course, the shear waves in the mantle have a lower velocity than the P-waves, so they're plotting down there, but mimic more or less the same sort of shape. But as they hit the outer core, well, they're not transmitted, so there's no shear wave velocity through the outer core. And then you'll see that there's a shear wave velocity plotted for the inner core. This can be detected from various conversions from P to shear wave at interfaces and then out again through some very detailed seismology using the coda parts of the seismograms, but we won't go into that here. Now, because the seismic velocity relates to density in part, these plots of P wave and S wave behaviour can be used to refine the density model for the Earth, and here's the density model plotted in, beyond that simple core mantle structure that we set up at the start. So that's the preliminary reference Earth model. Since 1981 there have been various tweaks to this. This is the first and establishes the general pattern very elegantly. So, we've looked at seismic waves, we've developed travel time plots at length, and we've used those to create a reference Earth model. We've seen that the Earth is concentrically layered, that the mantle is solid and the outer core is liquid. So this is a general model. Now, the usefulness of this general model is that we can look for deviations away from it. So we go back to the Prem plot for P waves. These are defining the expected seismic velocities for P waves in the mantle, the core. So the Prem model defines the expected velocity at every depth. Therefore, if we have particular records that deviate away from this, we can use these deviations to image detailed structure within the mantle. Essentially, these deviations away from a general model is the basis of a CAT scan, the sort of thing in medicine that looks for anomalies within human tissues, tumours. In the Earth, we can use these to look for Earth structure. And this approach is called seismic tomography. So let's see how this plays out. We've got an earthquake, we've got some receiver stations shown there by the purple blobs, and within the mantle, a slower velocity model picked out by that pale blue. So here we have a seismic ray path from earthquake to that near station, and it arrives on time because it goes through normal mantle. But now let's consider a ray path that passes through our slower velocity body. And because this ray path goes through the slower velocity material, it will arrive slightly delayed on its predicted arrival from the Prem model. And another one here that's also gone through the slower velocity body that will come in slightly late, and then one over here where the ray path has avoided the slower velocity body, so that comes in on time. So this is the basis of seismic tomography. And of course, we don't just use one earthquake and 4 stations, we use many. So the more earthquakes and receivers, the better resolution. Here we've got 3 earthquakes with their various coloured up ray paths. The ones that have gone through the lower velocity body we've marked as a negative arrival, in other words it's come in slightly late. The ray paths that avoided the lower velocity body we just marked as 0, they're on time. But of course here we've worked assuming we know what the body looks like. If we just plot the data that we've got, we know that there's a lower velocity in here. The more ray paths we get, the tighter the fit, the better we can image the velocity anomaly within the mantle. Now, the ability to do this depends not only on having lots of instruments, but also lots of earthquakes, and earthquakes in the right places. So there's a limit to where we can play these games. Nevertheless, let's look at some results. So this is from the IRIS website, and it shows a tomographic image for a swathe of the Earth. You can see from the curvature, there's 0 at the top of this coloured up diagram in here, which represents the Earth's surface, going down to 1800 kilometres at depth at the base. And you can see from the map at the top, this is a slice through North America and out into the Atlantic. And those various colours are showing these seismic velocity anomalies as deviations away from the predicted. So let's think about how this diagram works, and particularly the colour bar. This is a standard colour bar that moves from red to blue via yellows and greens, and those yellows and greens represent seismic velocities that are normal. The red colours represent areas where the seismic velocity is slower than predicted. The blue colours represent places where the seismic velocity is faster, and this is a standard convention in these diagrams. And the reason for that is, if the mantle is constant composition, then the variations in seismic velocity reflect the temperature which will impact on its density. Where the seismic velocity is slow, the density will be lower, and therefore presumably the mantle will be hotter. And in contrast, where the seismic velocities are faster, the mantle will be denser. So fast is cold and therefore shown in cold blue colours. Slow is hot and therefore shown in warmer red colours. So that's the convention. Let's look at a couple of examples now. And seismic tomography has been used a lot to image subducted slabs, plates penetrating from the Earth's surface down into the mantle. And these slabs are lithosphere, therefore they started cold at the Earth's surface, and they should therefore show up as blue parts on seismic tomography images. Let's look at an example here through Japan, which has lots of earthquakes and lots of seismometers, so the imaging can be spectacular. So these are 8 serial sections. On the right hand side of each is broadly east, on the left is west, and you can see these blue colours coming down from the Earth's surface going down beneath Japan. Japan's the bit on these diagrams shown by the solid black bar at the surface and occasional triangles which represent volcanoes. So the slab can be imaged really spectacularly, and we can get an idea of its dip and depth beneath Japan. We can also see hot mantle tracking back up towards those volcanoes. The other thing this diagram shows, sprinkled across the slab, are lots of little white dots, which are lots of microseismicity, earthquakes significantly less than magnitude 5 that are picked up by local seismometers. So we can see how the earthquakes relate to the downgoing slab. It's a really spectacular illustration of plate tectonics in 3 dimensions. Just to zoom in on that, here we go. Slightly blurry, a couple of these images with the cold slab going down with seismic velocities of P waves some 6% faster than predicted for the slabs and some 6% slower for the hot bits coming up beneath the island. But it's not only subducting slabs that can be imaged through seismic tomography. This is a compilation done by USGS across a chunk of North America, showing the substructure beneath Yellowstone, a mega caldera. And you can see red, slow seismic velocity zones tracking up through the mantle up to the crust, which the seismologists interpret as recording the heat engine that drives the Yellowstone volcanic province, and a bunch of others within this part of North America. So seismic tomography is developing into this fundamental tool for imaging the inner Earth. So, an introduction to global seismology for tectonics, leading to the idea of seismic tomography. Seismic tomography works as a concept because we're able to create a reference Earth model that has established the Earth has a broadly concentric spherical structure. Deviations away from these general seismic properties allows the tomographic process to work, and consequently we can image structures in the mantle such as subducting slabs and these upwelling hot parts of the mantle that link to volcanic provinces. These technologies are likely to become far more advanced in the future. The resolution in seismic tomography is largely down to computing power. And the more earthquake records that we can stack and the different types of wave, not just P waves but shear waves and more besides, that we can use in these approaches, the better and more refined our images will become. It's a frontier in earth science.